Hi there. Welcome to the second video in reinforcement learning in MATLAB. So in the previous video, we saw what reinforcement learning is and the environment that we will be using for reinforcement learning. So in today's video, I will go over that environment, what are the rules for the environment, what are the actions that are possible, and also we will implement, or rather we will import that environment in MATLAB and see some very basic actions. So here I have this environment that we will be using, which is the mountain car V0. So it is a discrete environment. By that I mean the actions are discrete, where you can either go left, stay still, or go right. So here's a cart, which is in this one-dimensional valley, and the goal is to reach this point. Now this cart can either accelerate to the right, accelerate to the left, and or it can do nothing or no acceleration. So if it only accelerates to the right, and also acceleration is fixed, there's a fixed value of acceleration that it can apply. So if it only accelerates to the right, it will go till this point and it won't be able to move further, something like this. So the way you would solve it is you keep on going forward, you go back, you go forward, you go back, and you generate some velocity and momentum, and that will help you reach this point. The states are basically defined by the position and the velocity. So the velocity could be positive or negative depending on which direction it is going. And the state value or the position value is the x value in this axis. So unfortunately, these gym environments are horribly documented. So I had to open up the GitHub repo for the details about the environment. So here I have, so here this is the gym's GitHub repo, and I've opened the mountain car environment. And here you can see the details. So the observations or the states that you will see are contain two values, the position, which is between -1.2 to 0.6, and the velocity, which is between these two values. And then you can apply three kinds of actions: accelerate to the right, don't accelerate, and accelerate to the left. Now, and this is denoted by 0, 1, or 2. So this is the basic goal. Rather, the goal is to reach that flag on the top that you saw. So the goal is to reach this point, and we have to decide what actions to take. Also, on reaching the flag, there is a reward of 0, and there is a reward of -1 if the position of the agent is less than 0.5. That is, if it reaches the goal, which is position 0.5, the reward is 0. Otherwise, there is -1, so there's a penalty. And there is a starting point, which is taken from a random value between this. And that's how you decide, well, that's how these are the details of the environment. Okay, so what we need to find, or the goal of this reinforcement learning, is to find a policy. Now, what is a policy? Policy is something that tells you, given a situation or given a state or an observation, what action to take. So here, given an observation would be given its velocity, given its position, tell me what is the correct action to take. And that's what we will implement here. So in this video, I'm just going to implement a random policy, just take random actions and see how that does. And the main idea behind doing that is I want to show you how to import this environment in MATLAB and also take actions from within MATLAB. Okay, so now let me open MATLAB, and let me also open a new script. Let me just dock this up. Great. And right. So let's create a test environment. Let's say my environment. And in this, I will load in the mountain car environment. So remember, anything that's Python, type py.gym, which is the library, and the command make for creating the environment. And the environment is called mountain car v0. So good. This creates the environment. And let's actually, you know what? Let's output this out. So when I create an environment, you should see that the environment has been loaded on to this variable. Just to show you, here's the output that you can see. Great. Now, whenever you load in an environment, the first thing you need to do is reset it so that things go back to its default value. And you type that by typing just reset. So let me just silent this line out and let's see the output of reset. So reset basically tells you, so the last output that you got is the observation. So this is the starting point of your car. So this is the X position and this is the velocity 0. So that is the position at which the car is starting, which is roughly the bottom of this valley. And this value will be random each time. So if I run this again, you see it's slightly different values. So this is a randomized starting position and the velocity is always 0. Okay, so this is what's happening. So we are, every time we run the script, we create an environment and we reset it. So we get a starting position. Now, suppose I want my environment to run for 100 steps. So by that, I mean, I want to take 100 different actions. I see observation, I take an action, and the car moves, and that's one step. So what if I want, say, 100 steps? So let me loop through it. And I define my policy, or rather my action, by this random policy. So I'll explain what I'm doing. Let me just type this out. 1, 2. All right. So first of all, this rand_i command generates a random integer between and including 0 and 2. So 0, 1, 2, it picks a random integer from 0, 1, and 2. And this is the size of my output. So it's a 1 cross 1. So basically a scalar. So this thing, basically this command just generates a random number between 0 and 2. So let me just show you that in command window. So I don't know if you can see. If I type this, you can see a random number was generated, say 2. Try it again, 2. Try it again, 0. Okay, so this is what that does. Int 16 is because there is a data type mismatch between MATLAB and Python. MATLAB has its own data types and Python has its own. So I want to convert the MATLAB data type to be something that's compatible. So I want an integer that's compatible with Python's. So I am casting it. So this takes the action. And then when we want to take the action in our environment, what we do is we call in this function or method called step. And in step, we pass in the action that we want to take. So my environment steps in with this action that we generated, which is random. So, all right, so let's loop through this. And that's it. It got done pretty quickly, but you can see like it generated a lot of outputs. So I intentionally left this line loud. By loud, I mean I did not put semicolons at the end because I wanted to show you the output. And so there would be hundreds of these outputs, like exactly 100 because we ran for 100 steps. And at the end of each step, what you get is the position, the velocity. So basically the next observation, you take an action. So in a state, you take an action you move to a different state. So that's the observation you get. The reward, it's -1 because you haven't reached it and you haven't reached the end goal, and false because this tells you whether your session has ended or not, or rather, like, have you reached the goal or not, or whether your episode has ended or not. So not so important, but the first two are important. This is the next observation, and this is the reward that you got. And there are like tons and tons, rather 100 of them. Great. So, okay, that's good. But what if I wanted to visualize what's going on? So let's do that. I make this line silent, and then I render out each frame by just calling the render command. And it's very important to note that if you render an environment, make sure you close it, because otherwise sometimes memory leak happens, and because we are using an interface between MATLAB and Python, and if you do not close the environment after rendering it, it tends to crash either MATLAB or Python. So make sure you close out the environment whenever you use the command render. Okay, great. So let's play that. Oh, it got done pretty quickly. And the reason was because this is far too few steps. So let me increase that. And let's try this again. And let me pull the screen over here. So you can see it's taking some random actions. Let's run it again and get the screen here. It's taking random actions, and it's not doing anything much, but it's taking random actions. So, well, let's put in one more 0 to see this again. Pretty quick, not doing anything. And this is exactly what we wanted to do. It should go up and back and then reach this point. But then right now it's just random action, so kind of doesn't make that much sense. But while it runs, I want to just go over the code again. First, we made this environment in MATLAB. Then we put it to its initial condition state. That means we reset our environment. And then we just like run over a bunch of steps where we randomly take an action, and then we step our environment in the direction of that action. So, and also we render it. So this is basically how a reinforcement learning, how should I say, loop works. But the idea is that we want to learn the correct actions to take. Right now, we were picking up random actions, but soon we will learn how to take the correct actions to pick, or how to learn how to pick the right action. And we will be using an algorithm called QLearning, and now I'm going to tell you a bit about it. Before I end this video, I'd like to talk about the algorithm that we will use to train our reinforcement learning algorithm, and that is QLearning. So let me preface it like this. So our agent, or our player, or our car in this case, sees the state, which is its position and the velocity. So that's what it sees. It doesn't see anything else. Now, based on this state, it has to take an action. So decide the action. So this is the main question, or this is what we need to find, that how to take, or which action to take. And like I already told you, we could either go left, right, or stay still. Now, the way we decide this is the way we take the action is by taking the action that gives us, or that has the probability of yielding the maximum reward. And that is called the Q value. So Q value typically this Q function takes in two variables, or two arguments. The first is its state and the action. Now, and then it gives a number. That number is basically tells you what is the yield of that state and action pair, or like what kind of final reward you would get with this. So let me just call it reward number, or just reward rather. And so for every state and every action pair, so there are like thousands of them or millions of them, you would have a reward associated to them. And all you need to find is which, so argmax over A of Q of S comma A. So for any given state S, which action gives you the maximum reward is the action that you would choose. So this is basically how QLearning works, right? So I'm not going to go over the details of QLearning. There are plenty of videos about it on YouTube and plenty of good resources. But here I have a wiki page on QLearning, and this is the main equation, and I will quickly explain how this equation works. So before that, um, so we construct, the first thing we do is construct a QTable. So QTable is basically states and actions. So on the column side, you would have all the states listed. Rather, sorry, the rows are the states, all possible states that you can have. And the columns are the actions. So in our case, it could be action 0, action 1, and action 2, and all possible positions. Now, we would have to discretize our states because in the range that we have, you could have infinite states because there are infinite points between 1 and 2. So we would discretize our states in buckets. And for every state, you would have all possible actions, and the value corresponding to these states and action pair is the Q value associated to it. So you initially start with all zeros or all random numbers, and after training, your Q table looks like something like this. So for example, for state 328, the action that is maximum is action 0 or north. So that is the one that would be picked. So this is how QLearning works, and this is how you take your actions depending on the Q values. Now, the way learning works is you first initialize your Q table to be zeros or some random numbers, and then you follow this equation, this particular equation. So let me just move this over a bit. Great. So here, let's say you are at time step t, right? So at time step t, you took an action and you got certain reward. Now, how you would go about updating that Q value for that state is you take in the old value, add in a term multiplied by a learning rate. So this is just like how neural networks worked, or any machine learning algorithm work. There is a learning rate associated to it. So similarly, there's a learning rate. Now this update consists of three terms. So the first thing, let's say, is the reward, like how much reward you got in that time step. So RT plus 1 indicates, so at time step t, when you take an action, what is the reward that you get? So that's the reward. Plus discount factor. Discount factor basically means how much you want to discount the future rewards by. So it's a number between 0 and 1 and has the effect of valuing rewards received earlier higher than those received later. Okay, so here, right, so I have discount factor. And then what is the maximum reward at the next time step? So you take an action and then and you will know the state that you're in. So you start from state ST. So let me state it this way. So you are at ST, and then you suppose you took action A at T, and that got you in state T plus 1. All right, so this is what you have. So let me place it like this. Right, so first you take in the Q value for this state and action pair. Then what is the reward you receive? So when you take this action here, you would get a reward. So reward would be say RT plus 1. So that's the reward that you get. That's the first term. Then the discount factor of the Q value of the next state, so the maximum Q value. So what you would do is, using your table again, you would try to calculate this thing, like which A yields the maximum Q. So which A, find out which action gives you the maximum Q, and then substitute that value over here. So the maximum possible Q value of the next state is the second term. And then you subtract it by the current value. So what's happening is, so you find the difference between the discounted maximum reward for the next state minus the current state. And then you add in the reward. That's the temporal difference. And this is how you update your Q value for state T. So let me go over this again. So what you need. So to update the Q value for state at T is, first you need this quadruple. So you need the state at T, the action that you took at T, the next state, and also the reward that you got. So you plug in the Q value, which was the old value at time T or at state T, and then you plug in the reward over here, and then you subtract the difference as well from here, and you add in the discounted reward of the maximum Q value at the next state. Okay, so I understand this is a bit complicated, but the good thing is that the equation is pretty simple, and this is exactly how we'll implement it. If you just think about it a bit more, you would see why is it so, because ultimately the way it works out is, so you have a current Q value, and then you add in with the learning rate the maximum reward that you could get in the next state. So this is like kind of like how gradient works, like how gradient descent works, but it's slightly different. It is just updating the Q value. So so this is how QLearning works, and this is the algorithm that we'll use in the next video. I urge you guys to check out the QLearning wiki page, and there are plenty more videos about it. So I'll see you again the next time.